Okay, we are starting lesson 2-4. You should have went to calculushelp.com and watched in the tutorials chapter 2, lesson 1, the difference quotient. Ignore the scribbles I have on the board. Okay, so that's what we're going to be working on today, is the limit definition of a derivative and the alternative form of the limit definition. And hopefully from the tutorial you understand a little better about here how the secant line, once we make that change in x smaller and smaller, how that secant line then soon becomes our tangent line, because we make the change so small that it becomes a tangent. So a lot of times students get scared seeing this f of x plus delta x. It scares them half to death, but just think of it in terms of x and y. It's the same thing. If you come over here, the slope of the secant we talked about before was the change in y over the change in x, and that's just our y2 minus y1 over x2 minus x1. See, when we do that here, if you go x plus delta x minus x, you are left with delta x. So that's why they have written right there delta x. And of course, if you plug x into the function, f of x represents y. Add that change in that, that's your y2. So don't let that form scare you. It's just a slope. Now the way we make that tangent line, the way we make the secant line become the tangent line is adding the limit to it. Because we're going to make that change, the change between those points, to 0. So it's just 1 point. The key between the two is adding that limit right there. So we're going to look at some different ways of how to write a derivative. So the key right here, the slope of a tangent line is called a derivative. Here are your most symbols. The most common one is this with the apostrophe right there, and it is read as f prime of x. Down here in the box you can see some other types of notations you will run into. We see the f prime again, or y prime. Another common one is dy dx. D dx of f of x, meaning just take the derivative of the function. Here is the difference quotient. And once again, here's another way of seeing the different quotient. So now instead of using a delta x, they're just using h's. So you need to be able to recognize that those are just the same things. Don't be intimidated by them, and you're good to go. So let's try our first example that we have here. Once again, I'm going to write the problem just to make sure the limit. I'm going to write f of x plus delta x minus f of x all over delta x. So the limit as delta x approaches 0, this is where students get scared. They're like, I don't know how to do that f of x plus delta x. Well, if I first asked, what is f of 13, what would you do? You're going to come up to the function and plug 13 in for every x. Well, now we're going to plug in x plus delta x. So here's my function. I hit x, so I must do parentheses. X plus delta x. Well, what's happening to that? It's squared, so therefore I must square this. I need to write the whole problem plus 2. So now I have taken care of this first part. Now we have to do minus. Well, we're going to minus the function. Well, what is the function? It's right there. Whenever there's more than one term, make sure you use a parenthesis. Or you can go ahead and distribute in. X squared plus 2 all over delta x. Now, I know you're looking at that thinking that is messy and ugly, and it kind of does look that way. So now we're going to do some algebra to clean things up. Keep your limit, because that is what makes it the slope of the tangent. FOIL this out, x squared plus 2x delta x plus delta x squared plus 2, FOIL in your negative, negative x squared minus 2 all over delta x. So now let's look at our problem and see what starts to cancel. Our x squareds are gone. Our 2's are gone. So now we're down to just this right here. And if I was to evaluate that limit, you notice I get a 0 over 0. So what should we do? And hopefully you thought of factoring. It's always your best thing. So we're going to factor out a delta x. If I factor out a delta x from the numerator, I'm left with a 2x plus delta x all over delta x. And what is delta x over delta x? That is just 1. Now I can go ahead and evaluate my limit and plug 0 in for delta x, and I get 2x. So this f prime of x equals 2x. And I know you're saying, well, that's not a numeric value. Well, it shouldn't be, because we haven't assigned an x value for you to find it at yet. So one moment. Okay, so going back to why that is a function and not an actual numeric value. We are no longer dealing with linear functions. We know this is a parabola shifted up 2. And you can tell, depending on where you pick on that parabola, the slope is going to be different. So it should be an equation. So now we're going to go to part B, and we want to know, well, what is the slope at -3? So over here, what is that slope? Most of you can see that, of course, we better get a negative answer, and it's pretty steep. So we evaluate f prime of -3 equals 2 times, and what are we plugging in for x? -3. So that slope is -6. So that's what we're saying. At -3, we have a slope of -6. Right, let's go to the next example and look at it, and hopefully they will make sense. The hardest part, oops, missing a marker. I can't slide it up. Let me find the missing one. Okay. So example number 2, we want to find y prime, which is just the same as finding the derivative. So we start with our limit. The limit as delta x approaches 0, I'm going to just write the whole thing f of x plus delta x minus f of x all over delta x. So here we go to plug it in. The limit, delta x approaches 0. Cover that up and focus on this. What does that mean? Well, it means I go to the function, and wherever I see an x, I replace it with x plus delta x. X plus delta x. There's nothing else there, so I'm done. So now I'm here minus f of x. Well, f of x is just a single term, so I don't need to worry about my parentheses. All over delta x. Once again, if I plug in 0, I get 0 over 0. So I need to clean this problem up. Well, I see radical, so I should automatically start thinking conjugate method. X plus delta x, now plus root x times the bottom by the same thing. Okay, now with conjugates, we just multiply. Keep your limit. I'm going to run out of room, so I'm not going to write it, but it's still there with it. I get x plus delta x minus x. Oops, I don't know why I wrote a delta. Minus x all over. Now don't FOIL that in. Leave it delta x times root x plus delta x plus root x. Look up top. Our x's wipe out. Now I'm left with the delta x over delta x, which is 1. Now I should be good to evaluate my limit. So I plug in 0, and I have 1 over root x plus root x, which equals 1 over 2 root x, because I add their coefficients, which are just 1, and keep root x. So the derivative of y equals root x is 1 over 2 root x, y prime. Next example is dealing with a rational function. Slide up. Okay, different notation here. Now it's a dy dt. Well, what happened to the x? Well, look at what we're writing in our function. We're using t's now instead of x's. So that's why it's dy dt. So we're taking the derivative of y with respect to t, whatever the variable in the equation is. Once again, I'll write the long way here, just delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So plugging into here. So I start here. And I write the limit as delta x approaches 0. Come to my function. 2 over. I see next, so I replace it with x plus delta x. You can do t's, sorry, I switched. That's the end of the function, so minus 2 over x all over delta x. All right, now we're really going to work on your algebra skills. We want to clean up this complex fraction. So we're going to look at the numerator, and we want to be able to combine those two fractions into one. So we need a common denominator. And remember, the way you get common denominators is through multiplication. So I need to times this side by an x. So I times the bottom times the top. This guy needed the x plus delta x. X plus delta x times the bottom. You got to times the top. I'm going to come right up here. I'm going to keep the limit. Now write it as one fraction. So I have 2x. Distribute in the negative 2. Minus 2x minus 2 delta x all over x times x plus delta x all over delta x. And I know you're thinking, how in the world does that look any better? Well, we've just wiped out those. I still have a complex fraction. I want to get that delta x out of the bottom, so I think I flip in times. So I flip it up, times 1 over delta x. So that's all 1. Just going to erase that because it's all moved up. Erase this. Let me help you see it a little better. So now I'm down to this fraction, and now I can see a delta x and a delta x. What will happen to them? They will eliminate. Well, not eliminate. They are 1. So now I have negative 2 over, and this time I'm going to FOIL in. I'll have x squared plus x delta x. Still have my limit. And now I should be good to evaluate it. So I plug 0 in, which wipes that out. And so the derivative of that function is negative 2 over x squared. Once again, we have it as an equation because it depends on the x value we pick. We'll change our slope because this isn't a constant equation, constant slope. Okay, we also have another form, and they call it the alternate form because it's how we can evaluate the derivative at a point. So if you look right here, we say f of c, because we know we're plugging in that c value, the derivative at a certain point, the limit as x approaches c of f of x minus f of c all over x minus c. So the best way to do that is through this example right here, and I need more room. Keep it so you can see it. So we are evaluating the derivative at 3. And there's our function. So my c is 3. So now I do my limit as x approaches 3 of f of x. Well, what is f of x? That is x cubed. Now we do minus f of c. So my c is 3. Plug it into f. 3 cubed is 27 over x minus c. So x minus, and once again our c is 3. Well, if I plug in right now, what happens? I get 0 over 0. So I know I'm going to have to factor this problem. And I know x minus 3 is going to be a factor because that's what I need to wipe out. And so some of you are probably wondering, well, how do I get the rest of those factors? Well, you could do the guess and check because you know this is going to have to be a squared. You know it's going to have to end in a 9 to multiply to get to negative 27. And then you could just kind of play foiling in to see what it would be, or you can do synthetic division. Set the bottom equal to 0, which is 3. Make my box, my numbers. So I'm taking everything from the numerator. 1, x squared is missing, so 0. X is missing, 0, negative 27. Drop the 1, multiply, 3. Add, multiply, add, and remainder 0. So those are my factors. So I know this was a plus 3x plus 9. So there's how this cubic factored right there. Now we get that to be 1. So now I can plug my limit in. 3 squared is 9, plus 3 times 3 is 9, plus 9. So we have a limit of 27 when x approaches 3, meaning the slope of x cubed at the point 3 has a slope of 27, which should make sense. On a cubic function, it looks like this. At 3, that slope is pretty dang steep, so it should make sense, and it is positive. So there you have it with the difference quotient and the alternative form to the derivative.